So in the upper right-hand corner, there are several buttons, one of which says either speaker view or gallery view. And I would recommend speaker view. I think generally is nicer when listening to people give presentations. Also, I'm going to request that people turn their cameras back on if they're able to. So initially we had pretty decent participation in that way, and recently have seen a rather precipitous drop off. Thanks, appreciate it.
Okay, how is everyone doing this morning?
Pretty good.
Hanging in.
Yeah.
It'd be good once this homework assignment's done with.
Yeah. Okay. Let's hope for some sun this afternoon or this weekend. Let's start off with, are there any questions about the class, about the homework, about where we're going, where we've been, anything like that?
Kevin, for ridge regression, when we talked about it on Monday, my question is, the point of ridge regression is if you have collinearity between your features, then you can't converge to a linear regression using least squares. And that's why you use ridge regression. But let's say instead you use a different featureization, different pre-processing step like MR, where you identify all the features that are independent of each other. And then in that situation, do you even need ridge regression? Like, I guess what I'm saying is, should you use ridge regression in your original data set, or should you try to figure out what are the features that are actually independent of each other?
So that's a good question. You're basically asking, one of the big motivations of ridge regression is if you have features that are very aligned with each other.
Yeah.
And so perhaps your data matrix is low rank, or nearly low rank, or ill-conditioned, meaning that the minimum eigenvalue of your data matrix is, or singular value, is way smaller than say the maximum eigenvalue. That is a reason why you would use ridge regression to basically protect yourself against these large deviations that can occur from small sort of differences in the data and large sort of deviations. But it's said another way, it's a method to, all things being equal, this loss function is flat in some dimensions. This is saying basically the same thing, and you're trying to basically add curvature to avoid that sort of ambiguity. And you're suggesting that, well, maybe we should just look at our data from the beginning and remove these features, or maybe choose one if they're collinear, or do perhaps dimensionality reduction, maybe do PCA on your data first and then do this. Those are all totally fine options. Basically, ridge regression is just the ability to do some of that on that sort of feature selection in a more principled way. It's a very sort of soft decision instead of like a hard decision of doing feature selection, and that's why we like it. And it's also advantageous from a theoretical standpoint of we can understand it. We can understand its bias variance properties, and it's just a very stable thing. But one thing is to see on the homework, and as you have been kind of practicing with, there's been a lot of questions on, like, one of the problems where lambda is equal to 0 and your plots aren't exactly matching what you're seeing on the homework. There's a question like that where lambda is equal to 0, you're getting a slightly different plot than what's actually plotted in the homework. That's exactly this case. When you have lambda is equal to 0, the matrices are ill-conditioned. and you're getting something that, depending on your solver, whether you're solving on, say, Linux or Mac or a PC, you might actually get a different answer because the underlying math libraries that are used, the underlying linear algebra libraries that NumPy calls out to. So you could have the same version of NumPy, but have a different MKL library, and you could get a different answer. This is because there's ambiguity. And in the face of ambiguity, it doesn't know what to do. It chooses one.
Kevin, quick question. Are we intentionally paused on recording?
No.
Okay, I'm going to resume it.
Okay.
Right.
Yeah, sorry about that. I didn't touch anything, but let's hope that doesn't, let's keep an eye on it. So ridge regression is just a way to add curvature to your problem, which has nice statistical properties, but a big reason why we like it is it also has nice computational properties. It allows us to compute things in a very sort of safe way. We don't need to worry about things blowing up or NANDs or anything like this.
Which I'm sure we'll talk about eventually.
Yeah, yeah. And we're going to talk about other regressions and regularization actually right now.
Okay.
But we're going to, later in the quarter, we'll talk about PCA and dimensionality reduction, all these sorts of things. So it'll all come around full circle.
Okay. And then just a quick question is like, you know, let's say you don't do ridge regression, you have this data set that has, you know, these dependencies. If you just ran it 100 times, created 100 different linear regressions, you should see different weights for each of them?
Yeah, because it's random. If each data set is random, you'll get different weights and everything each time. Yeah.
Okay, cool. Thanks.
Anyone else before we start?
Yeah.
Okay.
Sorry.
Yeah, go ahead.
This is kind of a throwback question, but there's this article on the bias variance trade-off that was posted next to the slides.
Yeah.
And it says that, well, this is like near the end of the article. It's talking about asymptotic properties of algorithms. And it says that as your training size grows towards infinity, your model's bias will fall to 0. And I'm a little confused why increasing your training size would change the bias of a fixed model.
That's not exactly true. That's not, I wouldn't even agree with that statement in general. I'd actually argue for the opposite. But some of the, for some particular models, that is true. Like if your complexity grows with your training size, like if if the polynomial grows, say, you know, some slow function of the number of data points, then that will be true. But only in that case. For any fixed complexity class, like you are having p-dimensional polynomials and your n is growing, your bias is not going to go to 0. Your bias is a constant. So I would, I disagree with that statement.
That makes more sense. Okay, thanks.
Okay, so today we're going to finish Lasso really briefly, and it's just another way of doing regression. But what we like about Lasso is that it encourages sparsity. So we say a vector is sparse if many of its entries are 0. So you might say, like, if a vector W is in 10,000 dimensions, we might say it's sparse if a very tiny fraction of those elements are actually 0. Like we said, one sort of motivation for this is that if W has, if many of these components of W are 0, then computing this inner product is, you just need to look at the non-zeros. And just from a storage point of view, you can store W as like a linked list or a dictionary instead of an array. Because if you have a bunch of zeros, there's no sense in allocating those floats to those elements. But the real reason we like sparsity is because of interpretability, not really computation. Where basically, if you have a number of features describing your house or whatever, you want to understand, you know, you want to look at those coefficients, because this is what a lot of people do. They want to understand, like, what are the attributes or the weights that are going into making these decisions or predictions. And so we talked about, you know, you could test all exhaustive sort of subsets if you wanted to find a 5 sparse vector. So meaning that you have 100 different features and you want to find the feature that uses just at most 5 of these to do the predictions. You could try all 100 choose 5 combinations and see which one performs the best, but this could be forever. This could take a very, very long time. So there's greedy sort of heuristics where you add one feature at a time, or you start with all of them and take one feature away at a time. These can sometimes work, and you can sometimes prove things about these, but often you cannot, and they can get stuck in a local maxima or local minima, and you'll be sad. So another idea is to use penalized regression or regularization. So we already saw one example of this with ridge regression, and what it does is it explicitly makes coefficients small, right? But it does so in a very particular way. What we analyzed last time was it sort of shrinks everything towards 0. It is trying to sort of rescale the weight vector in sort of in a nonlinear way, but it scales the weight vector in such a way that it's shrinking it towards 0. Not necessarily clamping to 0, but it's sort of shrinking it. And so here's this nice plot where for lambda very, very small, lambda small on your right-hand side, lambda large on your left-hand side. And so as lambda gets smaller, the coefficients get from larger to smaller, the coefficients get larger. So as I ramp up lambda, I can make these coefficients go to 0. And so this seems kind of like what we want. We want a lot of 0 coefficients. However, what we notice is that for any particular value of lambda, these aren't exactly 0. They're just small. And there's a reason to be concerned about this, as we started getting to last time. What you might do is just run ridge regression for some finite value of lambda. That sort of shrinks the coefficients in such a way that they're not going to be larger than they need to be. So this is sort of a good start. You're not going to have this, you're not going to have some huge coefficients. But what's really going to happen here is that if we had some sort of correlation, these collinear features, as we were just talking about, say bathrooms and showers, these might be extremely correlated. And for simplicity, let's say they're exactly correlated. So maybe every bathroom has a shower. This is not always true, but let's say it is. And so if that were the case, then basically I could put equal weight on the number of bathrooms or the number of showers. It just, from a linear regression standpoint, if I didn't care about the regression term or the penalization term, it just wouldn't care whether you're putting that weight on an equal weight on both or more weight on one or the other. And so what if we didn't include showers, though? Suppose we did this regression again, but instead of having both bathrooms and shower in our regression, now all we do is we have bathrooms. Now before, what's going to happen is that because they were collinear, if we take out showers, all that weight that was on showers is now going to transfer over to bathrooms. So in this plot, where this dotted line is the same, if we're going to threshold, say, our features and put them to 0, in this plot, when you're going both features, both the features values, the W that we would learn for each of the features below the threshold. It did not exceed some absolute value. But when we take out showers, this coefficient, because they were collinear, all the mass of showers gets transferred to bathrooms and is now larger than the threshold. And this is somewhat arbitrary. It's hard to sort of see these things with just looking at the data and to predict what would have happened if I do something like this. And this is very, very unfortunate behavior. We don't want this kind of behavior where if I take a feature out, it just puts a lot more mass than some other feature. We'd like something where the model sort of commits to one. If all things being equal, we'd like a model that prefers to use, if I can put equal mass on both coefficients or just double the mass on one coefficient versus in 0 on the other, we want a regularizer or a model that prefers the latter. We want to prefer a model that would choose to put all the mass on one versus split evenly over the 2. And so if we look at ridge regression, it's not going to do this. Ridge regression will not have this sort of behavior. It will not encourage it enough. But if we change our regularizer, we might have this behavior. And it turns out that Lasso instead of adding a L2 norm squared up here, we're going to add a L1 norm. And the difference here is just the shape of what this norm looks like. And just to review, when I have, this might be the first time you've seen anything other than the L2 norm. And just for review, we call a P norm. So the P norm of vector W is defined as such. We just sum up all the entries, we take it to the pth power, and we take it in the sum to the 1 over p power. So if for p is equal to 2, this is, of course, just your typical
Euclidean norm.
Yeah, Euclidean norm. And if p is equal to 1, this is your L1 norm, which just simplifies to something very simple as that, as just the sum of the absolute values of the coefficients. Now, to get some intuition about what these norms look like and why this lasso objective might encourage more sparsity than this ridge regression objective, it helps to think about what these norms look like and what's actually going on here. So in general, we can think of these as being penalized least squares. Okay, we're minimizing respect to W of some objective function that we care about. This is our training loss. This is what we're actually trying to do well, plus some constant lambda. So this is a hyperparameter or something that we need to tune based on a validation set, and some regularizer. And we've already seen how L2 norm squared, the ridge regression, can make your vector smaller, can shrink it towards 0. But the lasso seems to also kind of be doing that. It's going to always be preferring solutions with lower L1 norm. But how does that actually change things? And that's what we're going to talk about now. So a beautiful theorem, and it has to do with convex analysis. If you're interested in machine learning, I strongly recommend you take a convex analysis course or a convex optimization course. So Mariam Fazal teaches an excellent course in electrical engineering. Yintat Li teaches an excellent course in CSE. These are courses that are somewhat fundamental to machine learning. You're going to see optimization over and over and over in this class. If you do plan on pursuing machine learning as a career, I strongly recommend you take a convex optimization course. And so I'm not going to prove this theorem to you, but I will tell you that at least the result of it. This is not always true, but in this particular case, it is, say, morally true. There are benign conditions under which this has to be true. So, okay, let us consider our objective function here. What this red box says is that for any lambda greater than 0, so I'm going to fix some lambda greater than 0, and let W hat R be the solution. Okay, so fix the value of lambda, let W hat R be the minimizer of this penalized regression function. Now, for that value of W hat R, there exists a nu greater than or equal to 0, so some other constant nu, such that W hat R is equal to the minimizer of just the training error, subject to R of W being less than or equal to nu. Okay? This is saying that these two problems are actually equivalent. For every lambda, there exists a nu. So for every lambda, where W hat R is the solution to this above equation here, there exists a value of nu such that if I solve this problem, I will get the same W hat R out, which is quite remarkable that these things are related in some way. And this goes back to what I was saying before when I said very much earlier in the quarter, or like a couple lectures ago, when I said all things being equal, ridge regression is going to pick the one with the lowest norm. And this really makes that connection clear, because what this is saying is for every lambda, there exists some nu where I'm actually doing a penalized, constrained optimization problem. Because the first one, this is called a penalized objective, because I'm adding in the behavior that I want. I'm penalizing high norm solutions or high regularized, high values of R of W. Whereas this bottom one is saying, not penalizing ones, but saying it's constraining them. It's saying, I'm only going to look at W's such that R of W is less than or equal to nu. Now, of all those W's such that R of W is less than or equal to nu, I'm going to pick the one that minimizes the training error. And this makes it very clear when I say, all things being equal, ridge regression will pick the, all things being equal, meaning like the training error is the same for all the different W's, it's going to pick the one that has the smallest value of R of W, or the smallest value of ridge regression, or the L2 norm. And that's what's sort of making this explicit. Yes?
Yeah, hey, I've got a question which I was going to ask before you even wrote this on the slide, but so you motivated Lasso by suggesting that it'll find sparse solutions, and the L1 norm sort of does that, but the L0 norm seems like it does it more than the L1 norm, if that was your primary concern, right? And maybe this is a question for everyone else in the classroom as opposed to Kevin. Does anybody see anything wrong or that might like come up to be problematic if we use like the L0 norm as a regularizer as opposed to the L1 norm?
And when she says L0 norm, it's not really a norm, but what she means is W of 0 is equal to I equals 1 to D of the indicator that Wi is not equal to 0. So it is the number of non-zeros in W.
And there's certainly some relationship to the next slide, but also like this would directly do what Kevin was suggesting, right? The L0 norm actually says we are penalizing the number of non-zero weights that we have, that we find in our model.
Is it convexity? Is that the reason why you don't use L0, maybe?
So it's even worse than that, right? Oh. It's like not a continuous thing.
Okay, right.
But yeah, right. So right, you lose all sorts of nice properties that you had, that you would have for like the L1 or L2 norms. Yeah, right. Like in terms of optimization for one.
Yes. So like ideally what we want to do is minimize some objective that traded off, say, the sparsity, or say the actual number of non-zeros in W with the actual training loss that we have. That's what we do in an ideal case. And that's really what this is. These sort of greedy, trying to find the best subset, saying like subject to, I want to find the best 5 non-sparse vector, or 5 sparse vector, the best 10 sparse vector. And you can go back and forth between saying I want to find the best 10 sparse vector, meaning like minimize the training error relative to being 5 sparse, or you can add the objective to the training error plus some penalty times the sparsity level. And basically what this is saying, well, the L0 norm is not convex and it's not even continuous, so I'm not sure if this theorem is even true anymore.
I suspect it's not. Although maybe it is, but like not for the same reasons. You'd need a subset case.
Yeah. But the reason we're looking at regularizers in the first place is because we can't actually optimize this. We can't take the gradient of it. We can't actually compute this. This is a combinatorial optimization problem, which you can do sometimes if you're looking for a 5 sparse vector. I don't know, n to the 5 may not be too bad, or d to the 5, but and for typical values of d, that seems pretty impossible. And so what this is saying is that I just want to sort of get in your head that you can either think, whenever you see a regularization like this, at least intuitively, when you're penalizing some values of W, you should be thinking about, well, I can also think about this as a constrained optimization problem of, given that I'm searching over all W such that R of W is less than or equal to some value, I pick the one with the smallest training error. And this is true for convex regularizers and convex problems. And we're going to talk about convexity more in maybe this lecture. But the reason why I'm telling you this is because since this problem, the penalized objective is equivalent to the constrained objective, meaning that for every lambda there exists a nu, and correspondingly for every nu there exists a lambda. What we can say is then that we can think about this constrained optimization problem as a very intuitive sort of object. So what do these norms look like? So if we think about what the L2 norm looks like, if we say the L2 norm squared is less than or equal to nu, that's saying that the W must live in some ball. It lives in some sphere. That's exactly what saying the L2 norm is bounded by some constant says. And then what it's saying is this red here, equal potential surfaces, is exactly the contours of the loss function. So this point right here is equal to argmin W I equals 1 to n yi minus xi transpose w. So that is the minimizer of just the loss function. And then as you move away from that, this loss gets larger and larger, right? And as I move away, it's getting larger and larger. And then if you stay on one of these red lines, the loss is staying constant on that line. And so it's just like, think of it as a contour plot of like a contour map, that sort of thing. So then what this optimization problem is saying is that you want to subject to W living in its constrained set. So in this case, is cyan, subject to W L2 norm being less than or equal to nu, find me the minimum loss. And because these are contours, that's going to be exactly this point right here. Because it's saying, find me the point within the cyan set that has the smallest training error. And because these contour plots are getting larger, that is exactly going to be this point on the edge of this ball. Likewise, when you have the L1 norm, you can draw a picture. You can prove this to yourself. You just draw the L1 ball. I encourage you to do so. You'll find that it looks like a diamond. It is every point along here has the same L1 norm, the same sum of the absolute values of those points. And so in this case, though, it just happens that when I take to minimizing the loss function subject to R of W being less than or equal to nu, it ends up being this point here on the diamond. And what's important to realize here is that almost always, if you start drawing smooth, like what this contour plot was, if it looked like something else, some other contour plot, if you start drawing pictures, you're going to start realizing really quickly that you're almost always the minimum value of R of W within this diamond, or sorry, the minimum value of the loss function within this diamond is always going to sort of intersect at a point, one of these axes. And meaning that, like, because if you have any smooth function, like these contour plots, it's always going to, the spikiness of this L1 ball is always going to sort of like intersect at the spike, or one of these spikes or on an edge. In high dimensions, this is also the case. And so if we think about what these points are, this point right here is equal to 0 nu. That is the coordinate of that point. And if we have in higher dimensions, this is also going to be true. And this is what is really encouraging this sparsity. By actually forcing yourself to live in this O1 norm, and you're trying to minimize this objective function, you're trying to minimize the training loss subject to being constrained in this L1 norm, you're always going to, this L1 norm is really going to start constraining yourself and encouraging you to be on one of these edges or one of these points, and you're going to get a sparse solution. And this is not just these are just pictures and doodles, but in higher dimensions, you can actually prove, and under some pretty benign conditions, you can actually prove this very rigorously. You can show that actually you can, if there was some true W that was sparse, if you run this sort of risk penalization problem, there exists some nu or some lambda such that it will recover the most sparse W. It will recover the true sparse W that was there. And this has everything to do with this beautiful theory of basically these convex relaxations. Because as we were just talking about, you can kind of think about, if we think about this L0 norm again, you can kind of think about this as being a regularizer, which is just putting well, you can define this W0 as being the limit as the limit as p goes to 0. And what this object looks like, instead of like the L1 norm, which is like this diamond, the L2 norm looks like this ball, this object, as p gets smaller, is getting more and more spiky. As p gets smaller and smaller, it's getting more and more spiky. And at the limit, this is basically just going to be vectors. It's basically going to say, like, are you 0 or are you not 0? And you're equal to 1 if you are not 0, and you're equal to 0 if you are 0. That's what this is doing in the limit, this counting function. And so really what's going on here is that it's the L1 norm is the best convex relaxation of these one sparse vectors. And that's why this is all working. So this is a beautiful, beautiful theory. And there's a lot of very cool results that have come out in the last 15 years or so on this that I strongly encourage you to take a look at. High dimensional probability, compressed sensing, is a lot of the reasons why MRI works, and EM for imaging of like proteins and things like this. This is a lot of where the math actually lies and how we actually solve these things. It's really quite amazing. But it really came out of a lot of this kind of idea that we can do these convex realizations and they work. So that's all we're going to say about Lasso or regularization. So the only thing that I want you to remember, what I want you to know, is that just like with L2, for ridge regression will bias you towards small norm solutions, but not necessarily sparse solutions. Lasso will also encourage you towards small solutions, W is closer to 0, but in a particular way that will make this vector encourage sparse solutions, and has everything to do with the spikiness of this ball. And so that's what I want you to take away from this, that this regularizer, the regularizer that you choose here, and you do get to choose it, will have an impact on what your ending up solution will look like. You basically should choose your regularizer to bias you towards solutions that you prefer as a practitioner, or that like you believe your data should look like. If you really believe that your data should be sparse, it shouldn't depend on a lot of things, then it makes sense to do Lasso. If you just want it to be interpretable, maybe you don't believe that the data acts like this, but you just want a very interpretable solution, you can also do that. So yeah, There's many other regularizers that you can play with. You can do combinations of L1 and L2. You can do different structured sparsity, lots of different options here, and it's really quite endless. And this is where machine learning, a lot of machine learning is actually coming up with clever formulations of regularizers to get the behavior that you want, and then proving that that behavior is actually achieved by the regularizer that you proposed. Now, the last thing I want to say is, how do you solve this? So in ridge regression, we wrote this down, and then we showed that this was actually just another quadratic, and we had a closed form solution for what W hat ridge was. This objective, you'll find very quickly, has no closed form solution. And the reason why is because if you take the derivative of this objective, if we go through the same procedure as we did for ridge regression, take the derivative set equal to 0, you're going to find something very strange. That basically, first, the L1 norm is not differentiable everywhere. And this is because the function is not smooth. The reason why we like this regularizer is because it's very spiky. But that spikiness is exactly the reason why it's not differentiable. You can't differentiate it at 0, for instance. The derivative doesn't exist. And so there exist extensions of convexity analysis that extends the definition of gradients to subgradients. And so you can actually optimize this thing, but there does not exist any closed form solution. You have to use an algorithm to solve this. And we're going to see another example of this in just a moment. So just hold on for how you're actually going to get a solution to this W. We'll be talking about that over the next few lectures. And so with that, are there any questions on Lasso before I hand it over to Jamie?
And are people okay with me swapping slides in the interim? Okay, I think I'll do that.
I had a question, though I think someone else had a hand before me, so I should probably let them go first in the chat.
Oh, Yao, what's up?
I have a question on the slide page 31, the previous one.
Oh, sorry, I screwed up.
Yeah.
Is it all right? Can you ask the question without the slide present to the class?
The 31 is the one where I have the balls, the cyan balls, and the interest point. Yeah.
I just get confused about the .w hat because the one in the red box is .w hat without regularization, while the one above is with regularization. Are we talking about different W hats?
No, I'm saying that you fix the lambda, you'll fix the value of lambda, and then define W hat of lambda in the above one, the penalized one, and just like that, for that lambda, there is that W hat of lambda. And now I'm saying there exists a value of nu that may depend on lambda, such that the solution to the constrained optimization, let's call that W hat of nu, is equal to W hat of lambda. So I'm saying that there exists, for every lambda, there exists a nu such that the minimizer of both those things are identical. They are equivalent in that way. So for every value of lambda, the penalized minimization of W hat of lambda is equal to W hat of nu for some value of nu, where W hat of nu is the value of W that comes out of minimizing the constrained optimization problem. They're equivalent problems.
Okay, that makes sense. Thank you.
Barrage?
Yeah, what is the likelihood that I'm like maximizing to get this objective? Just like we did with like ridge.
Okay, so that's a really good question. Can you tie it back to maximum likelihood? So it turns out that you can't tie it back to maximum likelihood, but there is this beautiful theory of, well, I don't know if we're going to cover it, but you can read about it in the book, called maximum a posterior estimation. And basically this is, instead of doing maximum likelihood, it's a way of putting a prior distribution over W's And now when you maximize the posterior distribution, where the data your posterior distribution is basically your updated posterior. You started with your prior, then you saw some data, you construct your posterior, and the map estimate, the maximum posterior estimate, is the value that maximizes the posterior. So instead of maximizing the likelihood function, you're maximizing the posterior function. And for different choices of the prior, you get different regularizers. So if you're, so for ridge regression results from having a prior distribution that is equal to a Gaussian distribution centered at 0 with a fixed covariance, identity covariance. And Lasso results from a prior distribution being a Laplacian distribution, which is just e to the minus absolute value of W. Or e to the minus L1 norm of W. This is not the, I like this because it's beautiful and consistent. I don't like this because if you actually draw from a prior distribution, if you draw from a Laplacian distribution, they are not sparse. The vectors are not sparse. And so there's a weird sort of thing where it's like they're only approximately sparse. And so there's some sort of like strange stuff going on here. And basically the answer to make these consistent again is that like convex analysis is really playing a part here. Like the algorithm minimizing this convex objective is what gives you sparsity. Yeah, I don't have a better answer than that. But to your general question, go look at the map estimate.
Got you. And is there theory for other norms like L1 and L2? Is there like L3, L4, L infinity, whatever? Is that also, is there theory for that too?
Yeah, so like there's a general theory for P norms. Martin Wainwright has a book that's characterized these, a recent book. And basically, because that was basically a lot of his thesis work was doing this, was basically trying to understand how different regularizers of P norms in particular encourage different statistical properties of your estimators in convex sort of analysis. So yeah, there's a general theory for these things. And again, this extends to matrices as well. So if you've heard of matrix completion or the collaborative filtering, that's the same story goes to that as well.
Gotcha. Cool. Thank you.
Great.
Okay.
Cool.
Thanks.
All right. Cool. Okay. So thank you, Kevin, for that awesome description of Lasso and sort of what we've been talking about so far in the last few lectures, when we've been talking about using various linear models to make predictions, right? We've been talking about problems of making predictions which are real value, right? We've basically been saying, okay, for some number of bedrooms, for some amount of square footage, for some various other features we have, we'd like to make some prediction of sale value, right? And that has largely ignored the idea that we might actually care about making more discrete predictions, right? For example, if we're talking about weather, right, which I believe we talked about in like lecture 0, you know, we've largely been talking about, and apologies that this is for some reason this is going to be very bad if my pen is not working. Hold on 1 second, let's see if I can connect it. Okay. Okay, there we go. That's largely looking at problems of the variety that, like, perhaps we're trying to predict the temperature in a particular place, right? There are a large number of real values we might think about, and we're sort of trying to make predictions which are close, right? And that's fairly different from the problem, both mathematically and sort of practically, compared to the problem of, say, trying to predict, will it snow? Will it rain? The answer, yes, is maybe like the most likely thing for a random day in April in Seattle. But, you know, rain or not rain, or sun or not sun, clouds or not clouds, are sort of different problems than asking for a temperature, right? They're discrete. you know, certainly there's some measurement, right? And we're doing some cutoff of like how much does it have to rain for us to consider it to be raining. What percentage of the number of zip codes have to see at least some rain? But they're sort of, we think of these as much more discrete questions to ask and answers that we should give. Right? Okay, so I want to give another example. So if you show people who are sitting in an MRI machine pictures of different things, right? You can see that they sort of light up different parts of the brain, right? And if you, for example, are showing images of people to the subject in the MRI machine, compared to showing them a picture of certain kinds of animals, there are different patterns in terms of sort of where brain activity is taking place, right? And you might want to, from a bunch of these experiments, labeled perhaps by like actually putting humans in machines and like showing them images that you know about, and then seeing new brain scans of new people who are seeing some images you don't know about, predict whether those people were shown images of people or images of animals based on the information you have from these different brain scans, right? And if you are sort of guaranteed that the images that the people who you're trying to predict for are being shown either contain a person or an animal, right? This is a discrete decision that the model you're going to be producing would have to make. Okay, so this is the problem of classification as opposed to regression, right? And classification operates in the following worlds, right? So we imagine, where our goal is to learn some function f, again from our feature space x into y, right? And so far that's not at all different. That's not at all different from the problem we were thinking about before. But now we're going to think about y as being some discrete set, right? Which maybe takes on some k different values, right? And we call these target classes. And then the question is sort of, how do we do this, right? For many different reasons, this problem is somewhat different than the problem of trying to predict real values, right? So the loss function we generally talk about, or at least one of the loss functions we talk about when we talk about classification, is that we would like to make as many predictions correctly as possible, right? Or maximize the probability we make a future prediction correctly, minimize the number of mistakes we make, right? So we might say the loss function, sorry, my pen is not working today and I'm not entirely sure why. Okay, so the loss function that we often think about, right, is the one that asks whether we make a mistake on x or not, which is to say, we ask whether f of x is equal to y or not, right? Okay. So this is just the indicator function asking for a particular value x, whether our prediction that our function f makes is actually equal to the true class of the individual that is represented by x, okay? So then if we want to write the expected loss of f, right? L of f, right? That's just equal to the expectation over, does anybody want to guess whether we should break things into what we should probably do, right? Is think about y given x, the expectation with respect to x of loss of xy, right? Okay. And if we write that down in terms of this loss function we wrote right here, right? We see that we can write the loss function, one of the most canonical loss functions we use when talking about classification, as the expectation with respect to x. So we imagine drawing a new data point which is unlabeled, right? We don't necessarily have the information about which class it belongs to from our distribution. And then we think about the probability of the different possible classes it might belong to, right? And that's a conditional probability distribution. And then we think about the probability that the function we've picked, f, makes the correct prediction for a particular x, okay? And then if we just use, we can write this out, we can expand it. And write this out in terms of the different classes that we're thinking about, right? So this I going from 1 to k of the probability that the true class of a particular point x is equal to y, and then thinking about whether or not our prediction is class I or not. Okay. Okay. So suppose you knew this sort of conditional distribution, y given x, right? There's a natural question of like how, if you had all this information, how you should make some classification decision, right? If I have some fixed x, right? How would I minimize the expected loss for that particular x, right? And that's where the Bayes optimal classifier comes from, right? Which is this function just says, if you want to minimize your expected loss and you have perfect distributional information about p of y given x, what should you predict for a particular x? Well, you should look at the probability of the different classes, p of y equals y, given x equals x, and output the label y, or the class y, which maximizes that probability. Okay? So we haven't seen this precise thing before, right? Because it most naturally appears here. But this Bayes optimal classifier says, okay, you have a bunch of features about what about like yesterday's weather, and we're trying to predict whether it's going to rain tomorrow or not. So think about rain and not rain. Think about the probability distribution you understand about, given those previous features you saw, whether you believe rain or not rain is more likely. The way to minimize your expected loss is to predict rain or not rain, whichever one has a higher probability given the features you've seen. Okay. So if we're thinking about something like rain or not rain, that's a specific case, right? Where we're not just thinking about classification, but we're thinking about binary classification, right? Which just means that we're focusing on the setting where we think about the target classes, there being only 2 target classes, right? And that's the only difference that I've drawn in this entire slide, right? If we thought about I equals 1 to 2, right, there's some simplifications you could make in this precise writing down of the loss function, right? But this is, otherwise I've written nothing different here. So, this Bayes optimal classifier is a really nice thing, right? It tells you if you have some features and you're trying to make a prediction about a new data point x, and you actually perfectly understand the distribution of p of y given x, then the thing you should do is you should predict the class which is most probable given the data you see. On the other hand, right, most of machine learning doesn't operate in this space where we know p of y given x exactly, right? We generally assume we have some number of samples, right? We generally simply have n historical examples which are labeled for us, right? And from those examples, we want to make predictions, right? Or you know, analogously, right? We might want to ask how to estimate P of y given x. So I'm going to ask that you guys answer the following question in a moment here. Okay, so I'm going to ask that you fill out a poll in a second. Okay, so I'll be a little bit more precise about what I mean before I send this. Okay, so what is a natural estimator for P of y given x for a particular set of features? Right? So we have some x tilde, right, which we can think of as a fixed set of values for our features. And suppose we have exactly m samples which have the same feature values for all of my different features. And the question then I would like to ask is, if I want to know how to estimate the probability y equals 1 given these features. Sorry about that. I don't know what happened here. Okay. Sorry, everyone. Okay, good. Okay. So what is a natural estimator for this quantity? The probability our class label is 1 given these feature values and the data that we saw drawn from this distribution, right? And if, right, sorry, I'm having a lot of trouble today. Okay, if k of the m labels are equal to y equals 1, okay? So I want everybody to fill out, you know, just write down, jot down something quick in this poll everywhere I just sent, right? Which is just asking, what's a natural estimator for this data hat based on these n samples, m of which have the same feature values, if k of the m labels of those are equal to y equals 1. And are people able to answer that poll? Oh, cool. Yes, I'm seeing 4 answers. Okay, right. So the first 5 answers, 7 answers, have all said k over m. I have not yet seen an answer that's not that. So right. Okay. So as you guys suggested, right, k over m is a very natural answer. Right. And k over m is a very natural answer because that's the empirical probability of y equals 1 based on our sample, right? Great. Right. This is also equal to the MLE data star MLE given our data. Right? And you can show that in a number of different ways. Good. So that motivates more generally, right? If we're thinking about the probability of y equals y given x, the following thing, right? Thinking about, right, just the more general format of this for a general x, and for general y, is to think about, look at your data set, look at all of the data points in that data set which have exactly the same feature values, and look at the fraction of them that are assigned to class y. Right? That is the empirical probability that y equals y given x equals x. Okay, and then, you know, asking to output the maximum y, right, the maximum class membership for that empirical probability distribution. right? That's a very natural way to try to predict or try to estimate which of the different classes is the most likely one given the feature values we've seen. Okay, so I want to ask you, go to that same link and tell me what some of the issues might be with using this estimator, or using this function to predict y given x. Okay, there should be a new poll up now. Yeah, so the first one is, what if I don't see x tilde, right? We may not have a point with exactly the same features, may not have observed the data point previously. For some x, in the training data, f of x is not defined. All of these things, right? So these are all basically saying, we might be in trouble, right? Even in the previous case, this might have been the case if k, or well, if m were 0, right? The number of training data points we might see here, right? The number of possible training data points are there are 2 to the d many feature vectors. And that's problematic if m is smaller or much smaller than 2 to the d n, apologies. Right? Then we certainly won't have seen every example, right? So we won't know, we won't have any data for certain feature values if d is even modest, right? If we think about a relatively small data set, or even a reasonably large data set, okay? So if we want to make predictions for unseen inputs, right, we need to understand how we want to link together the different predictions we make for different x's, right? How we want to say that we assume either our data behaves or we want to make our predictions behave for different x's. Okay, so let's go back to the same process, the same slide that I was sort of belaboring when we were first talking about linear regression, right? The sort of recipe we want to use when talking about building machine learning pipelines is to first decide on a model, right? To consider a set of assumptions that we either assume our data behaves in a certain way, or that we want our particular estimator to satisfy. And then we will choose a loss function, pick the function which satisfies the assumptions we've made, which minimizes that loss function, and then use that function to make new predictions. Okay. So if we're thinking about binary classification, right, we need to make some assumptions or make some decisions about what we want to guarantee the model we're using for predictions will actually satisfy in terms of comparing x and y, right? So one option would be to use the standard linear regression model, which is to say we're either assuming our data actually satisfies or we want to make predictions that satisfy that y is a linear function of x, right? So, right? Unfortunately, right, if this is x and this is y, linear regression has a problem if we wanted to use it in this way, right? Which is that linear regression maps to points that don't make sense as probabilities, right? It maps to real values, and we really want to take real values and turn them into numbers that could actually be interpreted as probabilities, right? We're trying to estimate the probability of y equals 1 given x equals x. So we want to map, it would be fine to think about a linear function from x to y if we could somehow transform that into some function which actually maps between 0 and 1. Okay, so doing so, mapping from negative infinity to infinity, from negative infinity to infinity to 0, 1 is, such a map is just called a link function. Okay. So logistic regression, which is one example, the first example we'll use in this class of thinking about classification as opposed to regression, is a particular way of mapping from negative infinity to 0, 1, right? So we want to learn the probability of y equals 1 given x equals x using some function which first takes a linear transformation of our features, right? So it is doing something kind of like linear regression was doing initially, but then we have to squeeze negative infinity to 0, 1, so we can actually interpret these things as probabilities, right? And the particular link function sigma will use is this one right here, right? And this is a function which exists pervasively in machine learning, right? This is, it has several names: sigmoid, logistic function. There are various others, right? But that's where logistic and logistic regression comes from, right? And this function does what we would sort of hope it would do, right? So if we now look at the assumptions we're making, right? The probability that y equals 1 given x equals x and w, right? We've said we're assuming that that's just equal to sigma of w transpose x, right? And recall, these are just d-dimensional vectors, right? Both w and x are d-dimensional vectors. W transpose turns w into a column. And that's equal to 1 plus the exponential of negative w transpose x, right? And then if you say we're still in binary regression, right? Or sorry, binary classification. If we then look at the probability y equals 0, right? Well, if we only have y equals 1 and y equals 0, the probability y equals 1 and y equals 0 are just 1 minus one another, right? So we can write, you can check for yourself, but these are just, these are the two maps. These are the two maps that we would actually end up with, right? If we were talking about the probability that y equals 1, given the features we have and a particular weight vector under this particular modeling assumption, okay? And I want to note that the features here can be discrete or continuous, right? And this was true in our regression scenario before too, right? When we were thinking of W transpose X as the prediction we were going to make, right? There was no sort of categorical necessity that X be all of the features of X be continuous, right? We were talking about like number of bedrooms, for example, right? And that is not a continuous feature. And similarly here, we can think about features being discrete or continuous. Okay, so I want to stop and ask if people have questions, because I feel like I've been talking for a while and haven't heard from anyone. No? Yeah.
So basically, given some X, you're just gonna do this dot product W transpose X and then apply it with sigma. Mm-hmm. And then whatever you get, that's your probability. And then you just 1 minus that for the other one, straight up. For
binary, yeah.
For binary. Okay, so this probably changes when you have multi-class.
Yeah, if you have more classes than 2, right? The probability y equals I. That's just yeah, that's a different, right. This is different there. Yeah.
Okay.
Okay, so if we think about, and actually, you know, it's nicest to think about all of this stuff in terms of binary classification. We'll get back, I think, at some point in the class to talking about more than binary, but I think we'll focus on binary for now. Great. Okay, and part of the reason, yeah, you'll see in a moment for some of the reasons that we're doing that, right? So what this is doing intuitively, right, is that it's mapping, you know, we're just looking at this nice smooth function of x, right? If we're in a single dimension, we're mapping that value of x to something between 0 and 1. And there's some point at which this is equal to 1/2, right? The probability y equals 1 is equal to 1/2. And so values of x, which cause the sigmoid to be above 1/2, we would predict y equals 1. And below 1/2, we would predict y equals 0. If we were thinking about this sort of predictor that outputs the most likely y given x. Okay. So if we want to understand this function, the sigmoid, a little bit better, it's useful to understand sort of what the different terms of the sigmoid do, right? So just like when we initially had just this simple linear function, which is now the input to the sigmoid, right? W naught, right, has some property here, right? And if we look at these two plots, we notice that they seem to have the same sort of curvature, right? But they intersect the y-axis at different places, right? They intersect the y-axis at different places because W naught is sort of governing where they're intersecting the the y-axis, right? And then if you look at, you know, this particular plot, right, we'll notice that the y-intercept didn't change between the second and the third plot, right? They're the same here and here. And W naught is the same in both places. But this one got much flatter than these other two, right? Here we've got a fairly steep curve, and here this is a much more gradual one, right? And that's because W1, right, is actually governing that curvature here, right, for the sigmoid. Great. So the sigmoid for binary classes is just equal to this expression that we described before. Interesting. Okay. So if we wanted to write out the probability that y equals y given x equals x, sorry, y equals 1 given w and x, and we wanted to look at the ratio of these two things, right? That's equal to 1 over x of negative w transpose x, right? Which equals the exponent of w transpose x, right? And you know, if we want to look at this ratio and think about when we're going to predict the label 1 versus 0, right? When this is bigger than 1, right, we'll predict y equals 1. And when this is less than 1, we'll predict y equals 0. And the reason we'll do that is when the numerator is larger, that's saying it's more likely that the class given x and w is 1. That's larger than the probability that the class is 0 given x and w. Okay. So, I don't understand why this keeps, okay, there we go. Okay, so that's well and good. And I'm sort of suggesting that these things have some nice linear function, some linear functional form. And it's certainly true that at least in terms of the inside, the input to the sigmoid function is a linear function of x. But what does that sort of mean for the decision rule that we're making, right? If we look at the log of this ratio, right, the log of this ratio is just a linear, it is just a linear function. Okay. So what that means is if we look at the ratio between y, the probability y equals 0 and y equals 1 given x, and we have a particular w. Okay. Oh, sorry, I can't draw. Okay. Then this decision rule is linear, right? And this is the probability that y equals 1 given x equals x and w. And that's equal to sigma of w transpose x. Okay. So the recipe that we're talking about from previously, right, was that we decide on a model, and in this case, we've decided that we want to think about applying the sigmoid to some linear function of x, and then assuming that that will govern the probability y equals 1 given x equals x and w. Okay? And then we'll want to make the prediction that maximizes the probability of a class given x and w. Right? So the next part of our recipe is to think about a loss function, which we already did talk about a little bit, right? And then pick a function which minimizes this loss. Okay. So the loss function that we'll talk about is this conditional likelihood loss function, right? So we have a bunch of IID data, and I'm going to make a change here that I want to draw your attention to, which is that I'm now going to say, I'm still thinking about binary classification, but it's often mathematically and notationally very nice to assume the two labels we're looking at are not 0 and 1, but are -1 and 1. There's no sort of fundamental difference to these two problems, but it makes notation much easier. Okay, so you'll see in a moment why that might be. But let's assume that the two labels, the two classes we're thinking about are -1 and 1 rather than 0 and 1, right? So if we do that, right, this is in old notation, right, the probability y equals 0 given x and w, right? We're now defining that to be the probability y equals -1 given x and w, right? We are assuming that that is equal to this term right here. And similarly, right, the probability y equals 1 is equal to this term right here. Right? Okay, so then we can ask about computing the maximum likelihood estimator, right? What is the W, right, that maximizes the likelihood of our data, right, of seeing our data? Okay. So, right, this is same sort of thing that we've been doing from other lectures, right? If we want to talk about the MLE, the way we generally do that is we write down the probability of each of our data points, right? And because each of these data points is drawn IID, that's equal to the product of the probability of each of the data points individually, right? And then we can write this guy out just as this, right? And the reason, the reason that yi equals -1, 1 is particularly useful is that, if I go up one slide, right? So this equivalence right here, right? So if we allow yi to be either -1 or 1, then we can write this down in a particularly convenient way that doesn't sort of look notationally particularly different, right? So I want you to check that these two things are equivalent. That basically saying probability y equals y given x and w, that gives the same value if you use this expression as if you use these two expressions together. Okay. So, right. So if you actually plug in, you know, this was the expression that I claimed was equivalent to those two different expressions for the case where yi was equal to 1 or minus 1, right? And if you take a log, right, you'll find that these two terms are equivalent, right? That this one is equal to this one, right? Where you notice that you have the way it went from a max to a min was that when you took a log, you have log of 1 over something, right? So that's equal to negative log of something, right? And you can turn a max, that will cause a max to become a min if you drop the negative sign. Okay. Okay, so I want to finish this slide. Or I want to finish basically this analysis, or just give you this idea that, like, you know, we've been thinking about this MLE, right? Which was you might ask sort of whether there's a nice closed functional form of this term, right? And the short answer is no, right? Just like Kevin was talking about earlier on in class, right? When we're talking about Lasso, there's not sort of a nice take the derivative, you find a really nice closed form solution that just requires some like basic linear algebra solvers to solve, right? The way that we generally minimize this particular term, or, you know, given some data, we want to like understand sort of which W we want to use to make predictions, is by understanding something about sort of these individual, sorry, I don't know what's, one second. Okay. It's by understanding that the loss that we're looking at for the particular, for a particular W we're thinking about is just a linear, it's a nice convex function for each of our data points of our W, right? So we'll talk more about that next time, where we'll sort of give you more understanding of sort of what convexity gives you and how to solve any number of convex problems, including but not limited to thinking about how to find minimizers for Lasso, and also how to think about finding the W's for logistic regression, which will minimize your loss, or, you know, be the MLE for this particular model. Okay, great, and I'll stick around a few minutes for questions.
Yeah, I had a question. Yeah, for the example, like, I'm not seeing how, like, you know, assuming this is like your distribution, your y given x, this is like the sigmoid, like, how does that translate to, like, you get that decision boundary, you know, in that example that you have where you drew like this, like, how are you seeing that?
Yeah, so you need to do like the right transformation. And I think that there are some nice descriptions of this in the book. If like, I know I didn't label my axes appropriately, but you know, I would recommend looking in the book because they give like a careful description of this. Yeah, but I